Let's talk about coordination compounds. Coordination compounds get their name from coordinate covalent bonds. Coordinate covalent bonds are where one atom gives both of the electrons to the bond. So if you look over here, I've drawn the Lewis structure of ammonia, NH3, and you'll notice that it has a lone pair on the nitrogen. Now when we come over to the coordination compound, as illustrated here by this cobalt complex, sometimes they're called complex ions, we have a nitrogen and it's donating both of those electrons to the cobalt to form this bond, this coordinate covalent bond, hence coordination compound. Now, coordination compounds are divided up into two portions. We have the inner coordination sphere, and that's everything that's directly attached to the metal. And then we have the outer coordination sphere, and that's everything not directly attached to the metal, but still associated with this compound. So you may notice here that all of these ammonias, notice here ammonia NH3, are a neutral compound. So we have no charge for all of these ligands. Ligands are things that are directly attached to the metal. But we have a cobalt 3+, and so we have 3 chlorides here associated with it to balance out the negative charge. I just used the word ligand, and I should probably explain that. A ligand is just something that's attached to our metal, and generally we're talking about the transition metal elements, those D block elements in the middle of the chart. And often they bond with 6 connections, forming an octahedral geometry. But that's not necessarily the case. There are other geometries that coordination compounds can have. Let's look at a few more. We have a linear geometry, as illustrated by this silver complex. We have tetrahedral by this zinc complex. And we can also have square planar by this platinum complex. Now, you'll notice that platinum is a D8. It has 8 electrons because it's a +2. And a lot of times those tend to form square planar complexes. Tetrahedral complexes are not as common as our octahedral complexes, but they exist. It can be difficult to predict which type of bonding something will have, whether it will be tetrahedral or octahedral. Of course, once you know the formula, that kind of illustrates it pretty quickly because you'll have either 4 things attached or 6 things. But square planar and octahedral kind of share a similar geometry in that we're just missing the ligand below and above the platinum for the square planar. And so distinguishing between whether it will go square planar and tetrahedral can be a little bit of a challenge. And sometimes you just need to do the experiment to find out. So this is just a little introduction to coordination compounds, and we can thank an individual called Alfred Werner for coming up with their structure. And he did that before we really had proof using X-rays to examine crystals. And from that we can get the definitive structure of something. But it is interesting that Werner was an organic chemist, and he was interested in chiral compounds, that is, compounds that had a right and a left hand, so that they're non-superimposable on each other. Well, he took that and incorporated it into transition metal complexes, something that would not be possible with the theories of how these were bonding before. And furthermore, he did it without the use of carbon because people thought that carbon was where chirality came from. Now, a lot of compounds that have carbon in them do exhibit chirality, but it is not exclusive to them. And Werner showed that, and for that, he was awarded a Nobel Prize. And once we knew what the structure of these compounds were, we could think intelligently on how to design new compounds, and it really exploded the field of inorganic chemistry and made it much more popular, and we could actually do things in it. Now, a lot of these complexes have bright colors. They might be orange, which is the case for the first compound that I showed you. This particular compound is a bright orange. They might be red or purple or blue, various different colors, and these are used in artificial dyes or pigments for paints, and it's given us a richness to our life and really brought things into color because of inorganic chemistry and complex compounds.